Good morning to all the participants and also Ms. K. Tamilchelvi. I'm happy to welcome all the participants on the sixth day of two-week AICT sponsored faculty development program on cutting edge trends in deep learning approaches. And also I'm happy to welcome today's resource person, Ms. K. Tamilchelvi, Assistant Professor, Department of Computer Science and Engineering from the Engineering College. She is going to share her experience in the topic of convolution neural network today. I hand over the session to Ms. K. Tamilselvi.
Thank you, ma'am. Is my voice audible for you? If any interruption, kindly inform me so that I will correct from my side.
Okay, now it's audible.
Hope my screen is visible for you. So today we are going to step into a convolution neural network, that too mainly with respect to image processing. How convolution network can be used for image processing. So first we are going to cover the basics and basics of how convolution neural network work. What are the deep concepts that are behind the convolution neural network? Very simple only, it is not very complicated. And we are going to have some of the most popular CNN architectures. And afternoon session we are having the hands-on on it. And one thing I want to insist here is that the basic thing is convolution, how the convolution operation is made in the image, and how this can be used to get the feature extraction and other aspects. Next, we are going to have a current trends on it. That is today's aspect of this. Even though we are going to have a large coding on it, there is another Python package called Python library called FastAI. So I will have a demo on it also, how to. So in the afternoon session, we are going to have how the CNN architecture, pre-trained or pre-built architecture can be used for our application. We can go with the well-curated data sets like MNIST, CIFAR10 and other thing. And also, for instance, if you are not having the image, you have the problem, you want to provide solution for a problem, but the thing is that you are not having the image. This is one of the main thing we are facing in the deep learning. For instance, if the image, if the data is already available, it is not at all a problem. We can go ahead with our model and we will go with the training, testing, and go with the providing solution for it. For instance, you are saying that this is the problem I'm going to address with this solution, but I'm not having the image. I mean data set. Predefined data set or well curated data set or open data set may not be available. For instance, I will tell you, most of the medical image data sets may not be available for you, but you can create your own data set too. With the help of a minimal JavaScript code or Python code, you can generate your own data set and you can go with the data augmentation and you can build your own data set. This is very useful for going into the insight of how we can provide solution for the social problems that we are facing today. So these are the aspects that I want to cover in today's session. If any doubts or anything, you can interrupt me at any time, you can ask me. So this morning session is more or less which is equivalent to how this convolution operations are done, how this can be improvised and how this can be applied and what are the inner working of it. Because we know that already model is available, we will take the model and we will apply on our data set and we will produce the result. But we are not we are not aware of what is the internal working on it. So it is very essential to know how the internal things are happening. Then only things will go fine for you. So with this note, I want to go with the first convolution operation. Before going to the network, I want to know what is convolution operation. That is a basic thing. If we know those things, then convolution neural network is within 10 to 15 minutes, we can observe the things, and only those nuts and bolts has to be learned and things will find to fit in your solution. So with this, we will go into the convolution operation. So I will give you an example. Take an analogy For instance, you want to find the speed of the, for instance, the distance the flight have traveled. For instance, the flight has takeoff from the Chennai, it is going to Bangalore. After 15 minutes, I want to know how much distance the flight has covered. So today radar system has been done, is there in your airport thing. You can get the things out of it, and you can done it. But in your machine learning, I mean artificial intelligence, how this artificial intelligence can be used to predict or to find the distance that the flight have traveled. So in order to find that, what you can do, for instance, this is the time. For instance, at the time x, at the time t1. For instance, I'm saying that for at the time t1, this is the x naught be the distance. For instance, I'm saying at the time t naught, initially it is a takeoff, so it is a 0. For instance, I'm saying that it is 0. After 10 to 15 minutes, I am saying that it has traveled up to 10 to 15 kilometers or 100 kilometers, I am saying. After 20 minutes or 30 minutes, I am saying that it has covered for 200 kilometers. This is the thing. But the thing is that because of some noise in my data, I am not sure that whether this is the accurate thing or not. What will you do? If we are not having the accurate thing, we will go with the average, right? You will find what is the average, up the approximate distance. This is the, we will average the thing and we will say that this is the approximate distance that is covered by the flight. But if you take this approximate distance, what will you do? This is, for instance, if you take this aspect 1 by 3 of x naught, which is nothing but x naught plus x1 plus x2 by 3 is your approximate distance that is traveled by the flight. You can say like this. But there is a inner thing, inference, you have to have a look on it. If you take x, compare to x naught, x1 and x2, x1 and x2 has contributed more to your answer. Hope you can refer the things like this, because x naught at the takeoff place, during takeoff place, its speed may be little low compared to at the time t1 15 15 minutes or t2 equal to 30 minutes. So you can give the weighted thing for that. That is called as weighted average. Okay, instead of going with the equal average, you can go with the weighted average. So for each and every distance covered here, you are going to associate with the weight. In order that you are saying that this x2 is contributing more to me, this will be more accurate. This will be more accurate. That's why I'm giving more weight to this x2 compared to this w naught. This will be less, and compared to w minus 1, this will be less. So this is how your weight has to be done. So from that, weighted average will give you more approximate value than that of the average value. So this is what the real-time thing of convolution. You are going with your history. This is with respect to prediction of the speed or other things. This is 1D. This is 1D data, right? In 1D, you are going with the history. In that history, instead of taking the average, you are going with the weighted average. That too, in weighted average, the current data will be given more weight compared to that of the previous history. So this is what the convolution operation in the 1D case. So if you go with the, so this is what the thing I have given you. For instance, these are the weight 0.5. These are the weight I have given you. For instance, this is the time. This is the distance. For instance, I'm saying that this is the distance 1.90. In previous, these are the things I have assigned more weight to the current thing compared to that less weight compared to that. You can see that the weight is decreasing. If you find the weighted average, which is nothing but simply you can say that 0.5 into 1.90 plus 0.4 into 1.80, similar thing, you will get 1.80. So more or less, you will get the approximate value. This is called as 1D convolution. Now your data is 1D, this is called as 1D convolution. Hope you got that right. So if you want to find the convolution operation for 1D data, you are going for the history. In this case, in the history, you are going to give the weighted average. That's it. Very simple concept. So now we are moving to 2D concept. So 2D, this is an example, right? Actually, this is 3D because you are having RGB image. This is 3D. As of now, think that this is a 2D image, okay? So in 2D image, what you are going to see is that how this convolution can be done. I'm saying that in 1D, I have to take the weighted average of the history. In 2D, how I can done is that I have to take into account of my neighbors. For instance, I'm taking this is my pixel of interest. For instance, at any point for this, at least at this point, I'm saying that this is my pixel of interest. So in order to, for instance, take this, I want to find what is the value of this pixel G. In order to find the value of the pixel G, I can go with my neighbors. My neighbors are B, C, D, E, F, H, K, and L. Okay, here the weight is nothing but a kernel. That's it. Instead of giving the weight, here kernel will give you the weight. That's it. Clear with this? So for example, this is given here. For instance, if you have taken A, B, for instance, if you want to find weight of a particular thing, you have to move your kernel over that, and kernel will give you the weight, and you will find the value of that particular point of interest. So in 2D, the takeaway point is that you are going to consider the, so in 2D, kindly wait for a minute. Sorry for the interruption. So in the 2D aspect, we have to make sure that, so hope I am audible and I am sharing my screen. Okay, fine. So in 2D, instead of history, you have to take into account of the neighbors. So here weight is given by the kernel. This is what the mapping with respect to 1D and 2D convolution operation. We will go into deep how this kernel and input has to be mapped or hang over to the data and other thing. So hope you are fine with what is 1D convolution and what is 2D convolution. So in order to find a particular point of interest in 2D, I am going with my neighbors. That's it. In the weight is given by kernel. So, okay, we will go in depth of it. For instance, I want to find the point of, this is my pixel of interest or point of interest. I have taken this image. Assume that this is my image. I have divided this into pixel. Because the image is made up of pixel, I want to find what is the pixel value here. In order to find the pixel of interest here, I am going to consider my neighbors. If you take this corner, this is out of the boundary. Image, my kernel will move out of the boundary. That means my weight will move out of the boundary. So I will cover only these neighbors. Only these neighbors will be covered. So I have to make some changes. That is what padding and other things come into play. We will see these things in forthcoming aspects. Okay. So if you want to find the point of pixel of interest, you have to search for your neighbors. So all the side. Okay. So the next one. So this is how you have to go with the 2D convolution operation. So the next thing I want to see here, I'm saying that this is my kernel. For instance, I'm placing my kernel here. If based on the weight of the kernel, your image will be of different. I can say that there will be changes in the image. So for instance, if your weight is like this, in forthcoming slide, I will not tell you as a weight. In neural network, we are going to give it as a weight. In convolution neural network, we are going to give it as a kernel. So make sure that these kernels will give you the added value. So which is nothing but this is going to add with it and give you the value. If you see the formula here, see here, this is what the thing. It will take the pixels value and it will multiply with this. See here, A into W, and it will provide the sum of it. A into W plus BX plus, if you place your kernel here, that is AW plus BX plus EY plus FZ. So this is what the value of this pixel of interest. So you will find the neighbors and you will take the, you will find the neighbors and you have to take the neighbors and you will find the multiplied value and you have to find the sum of it. That is what the value of that particular pixel of interest you are going to calculate. The weight is given by the kernel. So if you see here, now my kernel is 3x3 kernel. Here, see here, this is a 3x3 kernel. So if you, So this is a 3x3 kernel. Now your image, this 3x3 kernel is more. So this is a 3x3 kernel. This is moved over your image. If you are moving over this image, this the value will be added. This kernel will give you the blur image. Next, if you take this kernel of this way values, if you impose on this image, this is called a sharpen image. If you can say this filter, more or less, these kernels are also called as filters. If you are saying this blur filter, for instance, if you take the Photoshop, for instance, if you want to blur the image, it is in background. This is what the thing happening. Just it is applying this filter. Here the kernel is moved over it, and the value of it will be reduced, and because of that the blur will be, see here, this is blue here, this is white here. It will take the RGB value. Simply this pixel is nothing but will give you the RGB values, right? Here it is a blue. If you want to calculate the pixel value of this image, for instance, if you take a pixel here, this is a blue color here, but if your surrounding is white, it may contribute white color so that it becomes a blur image. Hope you got the things right. So you can you may ask, since the values are positive, it may go add the things, right? You may think like that, but the thing is that they are different, right? This is blue in color, these are white in color. Surely there will be a reduction of pixel value. If the pixel value reduces, color also varies, so you get the blur image. This is what in the some of the editing softwares like Photoshop will do like this. If you apply blur, this is what the internal thing happening in that. If you want to sharpen that, what you have to do, you have to, for instance, if you want to sharpen a particular pixel, if you want to sharpen that, that has to be positive and the remaining thing has to be negative, because you are going to multiply and add the thing, right? You are going to aggregate that same wx plus same thing, summation of wx. That's it. Here x is the input, w is a weight, summation. Same thing you are doing. If you want to sharpen that particular pixel, what you have to do, that point of interest pixel has to be positive. See here, remaining things are 0, remaining is negative. So if you want to sharpen that particular value, remaining things will become less intensity, so particular point will be sharpened. So this is a sharpen filter. If you take and deduct the edge filter, this is called as edge filter. If you see the edge filter, see here, you have given the values as -8. If you apply the same concept, summation of wx, if you apply here, what will happen is that these values, this is a negative thing. If you go with a negative thing, it will go with it will reduce the value. If you reduce the value, it will go to the gray and I mean, so instead of RGB, it will go into the binary form, that is a black and white form. That's why you are able to get the edges of it only. So by default in 2D convolution, this is a edge filter, this is a sharpen filter, this is a blur filter. This is a default filter that are available. You can experiment with these things also. But in convolution neural network, if you provide this, you are going to provide only the size of the filter. These weights, explicitly you can provide the weights if you want. By default, these weights are learned because these weights are learnable parameters. Here the weights are nothing but kernel. I cannot say that use 1, 1, 1, 1. If you have 3x3 filter, if you are saying that, you will provide only the size of the filter alone. For instance, if you have given filter size equal to 3, means it is an implication that it is a 3x3 filter. But you are not provided, explicitly given an option to provide this is the value. For instance, I want to provide, if I have given 3x3 filter, if I want to provide these are the values of the filter, this is not given in convolution operation. This is what the core concept of convolution network, CNN, where it is going to learn the thing. So based on this filter value only, it is able to learn the features and get the things out of it. But explicitly also you can give on it. So this is what the complete convolution operation. So this is how you can move the your kernel, slide the kernel horizontally and vertically. This is how you will get the pixel of interest. You will get the value for pixel of interest. As of now, we are not concentrating on padding and strain or other aspect. Make sure that I am getting the value for these pixel with the help of kernel. That's it. With the help of neighbors. With the formula of summation of W into X. That is the thing we want to know out of these things. Okay. So these are the things. These are the things we have seen as of now. So, for instance, if it is a grayscale image, I am saying that there is only two channel, black and white. If you go with the 3D object, you have three channels. So here channel is nothing but how many, based on the color of the image, you can say that it is a channel. Channel is nothing but based on if RGB is a channel. So R will have its own value, G will have its own value, B will have own value. Because of these combination of this value, you are getting the color. So here three channels are there. So for instance, if you are doing a 2D convolution, 2D convolution is nothing but your matrix is 2D, right? 3 cross 3 is a 2D matrix. Am I right? Your kernel is a 2D. Now your filter is a 2D. You are applying to 3D thing. If do that, what will get? Finally, you will get the 2D also. See here, my input is 3D. See here, I have three channels and I am applying the filter. You see here, this is a red layer, green layer and blue layer of my input. I can say that this is a 3 channel. The depth is 3. Can I say like this? The depth of my image is 3, meaning that it has 3 channel. If you place a kernel like this, or I can say that the filter or a kernel. If I place a kernel here or a filter here, it may not penetrate into each and every layers. Please have a look on it. It will move only slides over horizontally and vertically, not in the other direction, that is inside the depth. You may ask, first it will slide over the blue layer, then to the green layer, then to R layer. No, that method is also available, but by convention, this will not go into the depth. So what will happen is that if you have given a 3D input also, if you provide the filter, even though you are saying that it is a 3D filter, it will provide you only the 2D output. Kindly map this. If your input is 3D, okay, you are saying that your filter is also 3 cross 3. You are saying that it is 3 cross 3. If your channel is 3, that filter will also act as a 3 cross 3, 3D filter. Are you getting the point? Your input is 3D input because it has 3 channels. RGB, that's why 3 channels. Next, whenever you are saying that you are applying on the 3D input, if your kernel, although it is 3 cross 3, it will always denote with the depth of it. So you are saying that 3 cross 3 cross 3, this is my filter size. If you apply on it, what will you get is that it will go with the scanning of the things with the depth, but it will not penetrate into it. So it will provide only the 2D thing. So final, you will get a matrix alone. That is 2-dimensional matrix alone. Hope you got the things right. So that is called the 2D convolution with 3D filter. So this is the input is 3D. The filter is also 3D, but the convolution operation that we are performing is 3D. You can ask 3D is also available. I'm saying that, but in general, if you go with the VGG, ResNet or AlexNet, whatever the in architecture, whatever the things that are present, they are going with these aspects only. They are not going with the 3D convolution. They are going only with the 2D convolution, what we have seen already. So this we are going to slide vertically and horizontally, not along the depth. Because I'm saying that the depth of the filter is same as that of the depth of the input. For instance, if I am saying that my input is 3D, if my depth is 3, I'm saying that my filter is also going to be 3D. So here I have given you only one filter. Is it possible to have multiple filters to the same image? Yes, it is possible. So see here, we have already seen some of the default filters like sharpening filter, blur filter, edge detector filter. If possible, you can go with it. For a single image, you can apply multiple filters. So each filter will give you the 2D output. So see here, for instance, take this blue is the blur filter. This pink is a sharpen filter. This next color is a edge detector. Assume that this is a edge filter. If you apply all these filter on the same image, a single image, you will get a, a 2D input. Am I right? Since we have already told that even though if your image is 3D, if you apply the filter, you will get a 2D thing. So that's what again, each filter applied through 3D input will give you a 2D output. Now what you have to do, each filter will give you an output, right? So combining the output of multiple such filter will result in a 3D. Now we will get a 3D output. Here the depth is nothing but a number of filters. That's it. So you will get the things once I have completed these things, you will get the things out of it. As of now, have a clear indication that if your input is 3D, if your filter is also 3D, you will get only the 2D output. So if you are applying a single filter, you can apply multiple filter. So as usual, if your input is 3D, your filter is also 3D, output is 2D. But now I am having multiple filters. So each filter will give you one 2D output. If all the three, for instance, in this case, if all the three 2D outputs are combined, you will get the 3D because I have three such 2D images. That is what the depth here. So now it is 3D output. So with these things, hope you got the things out of it. Next, what are the basic jargons that are present? So here the input width, height and depth. So this is width, this is width, this is height and this is a depth. Depth mostly is nothing but the number of channels. So if you take this example, so this is a depth of it. So we will see what is width and height, which is nothing but a matrix, that's it. This is height and width is nothing but the matrix. Then depth will give you the number of channels. Then output also. If output is 2D, width and height. If output is 3D, you will have width, height and depth. Depth is always think that depth is nothing but a number of filters. If it have more than one filters, you have the number of filters. If it is a channel, you go with the number of channels. That's it. Next one, number of filters. This is spatial extents of the filter. That is if it is 3 cross 3, 5 cross 5, 6 cross 6. This is called as F. Whenever I am saying that F is nothing but what is the size of that filter. Whether it is 3 cross 3, 5 cross 5, it is configurable, it is hyperparameter also. It is under our control. The number of filters, how many filters you want to impose on a single image. That is also hyperparameter, that is in our control also. Then we will go into padding and stride, how this neighboring collection of neighboring information is affected because of that corner places. That can be overcome with the help of padding, and you have a stride in order to avoid the number of computations. We will see what is these thing aspect. So as of now, depth, you have got the things in the input. The depth is nothing but number of channels. If you go with the subsequent layers based on the filters, number of filters, you will get the depth. So height and width, you will got the things from the image itself. So spatial extent of the filter is nothing but size of the filter, whether it is 2 cross 2, 3 cross 3 or 5 cross 5. So the number of filters, how many such filters you are going to apply on the image, whether it is 1 filter, 2 filter or 3 filter. Then padding and stride. So we have to calculate on this. Based on this only convolution layer will works on it. Okay, first we will see how will you calculate the W0, H0 and D0. For instance, I am saying that this is my pixel, this is the kernel RAM filter I have applied here. So if this is the case, as of now I am saying that this is the case, this will be the point of interest. Am I right? So this center will be the point of interest. So these are the neighbors. see here, I have got this. I have moved the kernel, I have slide the kernel. Now this is my point of interest. I have taken my neighbors, aggregated it and find it. Same thing you will do that. If you see that, for instance, if my image is, this is 1, 2, 3, 4, 5, 6. My image is 7 cross 7 image, but if you see after convolution, I got 5 cross 5. So I hope you got the things right. After convolution operation on 7 cross 7 image with 3 cross 3 filter, my image is 7 cross 7. My spatial extent of the filter is 3 cross 3. After performing convolution, I got 5 cross 5. There is a reduction in size of the image. This is because I cannot accommodate the corners, these corner pixels. So this corner, if I go with, if I have placed my kernel like this in the corner pixel, this is out of the boundary of the image. So this is not good. So in order to avoid that only, we are going for padding. Hope you got this thing. So if you apply this like this, you will get 5 cross 5 images after convolution. For instance, I have given a padding of 1 means in all the direction I have 1 rows and 1 columns of cells. So now this is what the thing. If you can fix my thing here, my kernel here, you can get the things right. So if the same 1, 2, 3, 4, 5. So in order to avoid this, you can go with the padding. Okay, so because I am not able to place my kernel at the corner points. If I go with the corner points, there is a no image because it crossed the boundary of the image. In order to avoid that, I will go for a padding. I will give you an example here. See here. See here, this is my thing. For instance, this is the output I have got. For instance, if my kernel is like this, if my kernel is bigger, if my kernel becomes bigger, surely there will be a reduction in the size of the image. Okay, for instance, this is your image. If you have gone with the kernel size of what is this 5 cross 5, whatever the to a point of pixel of interest, it has to cover all the neighbors. Then only it will get the aggregated value and provide the value and slide over it. So we have to take care whether I am crossing the boundary of the image. In order to avoid that only, we are going to give the padding. So we will go with the padding. As of now, if you have a point that with application of the kernel to your image, after convolution, there will be a reduction in size of the image. This is one takeover here. So how to maintain the same size after the same size image after the convolution is the next point we have to see. If the kernel size is very large, mostly your image size will be reduced. So how will you find the width of it? So width of final width is nothing but width of the input minus number of filters plus 1. Similarly, for height also you have to find like this. So for instance, if you're saying that it is 5 cross 5, for instance, I am saying that this is 5 cross 5. Your image is, assume that your image is 7 cross 7. You have applied F is, hope you know that F is nothing but a spatial extent of the filter. Now my image is 7 cross 7. So for WI, I will substitute 7 minus F. F is nothing but 3 cross 3 filter. I am saying that. So 7 minus 3 is what? 4. 4 plus 1, 5. That is what we got here. Hope you got these things right. For instance, if your image is 1, 2, 3, 4, 7 cross 7, if you have applied 5 cross 5, so 7 minus 5 is 2, 2 plus 1, 3. That is what you got the output. So this is the output, width and height. Width and height mostly it will be equal. So this is how you will calculate the width and height of the image after convolution. This is very simple thing. So if you apply a bigger kernel size, your size of the image will reduce to a large extent. So in order to maintain the size of the image, what the input has been given, you have to go for padding. Okay, so in order to go with that padding, see here, assume that this is my original, whatever. In padding, what I will do, I will add zeros to these pixels. So this is 1, 2, 3, 4, 5, 6, 7. Assume that I have given the input of image of size 7 cross 7. If I want to apply a kernel of 3 cross 3. So in order to find the pixel of interest value for this pixel, I have to slide my pixel over this. I have to place my kernel over our filter over this. If you see here, the padded values makes into account because of this corner pixel. So you can slide like this horizontally and vertically, you will get these things. Okay. So by apply padding, you will retain the input size same as in the output after convolution. So in order to find the output width of this is wi minus f plus 2p plus 1. So wi, hope you know that. For instance, it is 7 cross 7 means 7 minus, if it is 3 cross 3, so 7 minus 3 is 4. Here I have used padding of 1. See here, I have added 1 row in the top, bottom, left and right. So 1. So 4 and 4 plus 2, 6. 6 plus 1, 7. So same size is retained. So this is how padding helps to retain this. This will not contribute anymore because this is 0, right? This will not affect you anymore. So adding 0 to anything will not give you any difference in that. So this is how padding helps to retain the size of the image. So the next one is stride. Stride will help you whether I want to move my kernel step by step, or I can skip the pixels. For instance, I am saying that I have placed my filter here. So this is my pixel of interest. Then what will happen? So I have calculated my pixel of interest. Next, I will move my filter here. After moving my filter here, see here, I am going to find, now my pixel of interest is here. So what is happen? I have left one thing. Okay, so you will define the interval at which I want to apply. If you apply the higher stride, the output will become smaller. I can say that mostly the max pooling and other things will give you the will use the stride in order to reduce the size of the image, because if size of the images increases and dimension of the images, I mean number of computations will be more. If number of computation, number of parameters also becomes more. Mostly parameters will not depend, but number of computations will be more, because in order to avoid that only strides come into play. So for instance, my wi will be 7 cross 7. I have used a filter of 3 cross 3. So 7 minus 3 plus 2 into p. Here padding is 1 means, for instance, I have used a padding of 1. Padding of 1. Then stride of 1. Here the stride is nothing but 2. If you have skipped to 1, you have to use 2 plus 1. So you will get 5. So W1 7. 7 minus 3 is 4. 4 plus 2. 4 plus 2 is 6. 6 by 2. I have used stride 2. If you want to skip one cell, you have to give stride of 2. So 6 by 2 is 3. 3 plus 1, 4. Finally, you will get a 4. So in order to reduce the size of the thing, for instance, after something you have done you have extracted all the features of it, you want to reduce the computation, you have go for the stride and other things. So this is how we have computed the depth is nothing but number of filters. So depth of the image is always the number of filters. As of now, we know how to calculate the width, calculate the height, and calculate the depth. In general, in all the VGG, or if you take other networks, depth is always equal to the depth of the input. So which is nothing but a number of filters. If you have used 10 filters, the depth is going to be 10. Okay, so this is how you have to calculate the basic jargons of CNN. So this is what the thing, this is simple formula, this is how the internally things are working on it. So these are the basic things. If you have any doubt on these things, you can ask me. Any doubts? Take a minute, and if any doubts, you can ask me.
Ma'am, can you hear me, ma'am?
Yes, sir. Ask your question.
What are the various kernels we use in convolutional layers, ma'am?
Sir, in convolution, you are going to specify only the size of the kernel only. The weight will be updated. That is what the learning thing in the convolution neural network. By default, if you are saying that there is a blur filter, or I can say the sharpen filter, these are some of the examples. Oh, so in
Okay.
convention, in practical, you are going to specify, for instance, 5, 5. If you give filter size equal to 5, 5, by defaultly, it will randomly fix some value. Then it will go into learn those values. That is what the thing happening internally. It is equivalent to weight in the feed-forward neural network. So there is no fixed value for any filters. So there are certain filters like blur filter, sharpen and edge detector filter. These are the certain filters by default present in the convolution neural network.
Okay. Okay. Thank
So
you.
there is
Yeah.
no specific filter. Please make a note of it. The learning is happening only in the filter. Learning weight is the important concept in CNN. You can map this with respect to learning the weights in the feed-forward neural network.
Okay. We can use Gaussian kernels, no, ma'am. What is the
Yes,
specific reason behind Gaussian kernels?
sir, with respect to if you go with the signal processing, you can go with those things.
Okay, ma'am. Okay. Thank you, ma'am. Thank you.
Okay, sir. Any more doubts? Okay, we will proceed with the next concepts. So now we are stepping into the convolution neural network. As of now, we have seen the convolution operations and what are the basics things that are present. Now we are moving into the convolution neural network, how these things are present, how it is related with, what's the relationship between convolution neural network and uh, feed forward neural network, or I can say that fully connected. Always please have a look on it. Feed forward is equivalent to fully connected neural network. So if you see here, okay, we will start here. So we have seen many architectures. In first architecture, we are going to see what is the relation between the convolution neural network and the default other fully connected network. Hope we have learned that in fully connected network, see here, for instance, these are the neurons. Assume that these are the input neurons. Sorry, these are the hidden layer, first hidden layer neurons. You are providing the input. Each neuron, if you take this neuron X, this neuron has to be connected with, this will interact with all the neurons and will get the aggregated output. That is what the pre-activation is. Am I right? For instance, if you want to find the result of this neuron, first you will find the pre-activation, then activation. Here the pre-activation is dependent on all the neurons that is present behind it. So this layer. So if you want to find the pre-activation, that is aggregated sum, what you will do is you will find the weight of it, take what is the output of this neuron, you will multiply it and you will provide the sum of it, then you will add the bias. That is what the summation of Wx plus B. So summation here, take all the neurons, weight into input plus weight into input of other neuron. How many neurons are present? You have to take all the neurons into account. But if you take in convolution neural network, there is a sparse connectivity. You are not taking everything. You are not taking only the neighbors. This is a one relation difference between convolution and the fully connected or feed-forward neural network. Instead of taking everything, for instance, if you want to find a pixel of interest, want to find the value of a particular pixel of interest, what you are doing, you are going with the convolution operation. In convolution operation, you are taking only the neighbors, not the other things. But in fully feed forward network, you will take all the neurons that is behind you. This is one thing. Because of this, there is a sparse connectivity. Because of this sparse connectivity, there may be advantage and disadvantage. One advantage is that you are going to have a less number of parameters. If you take fully connected network, it will go with a more number of parameters. If you go with a more number of parameters, back propagation is very difficult in feed forward network compared to CNN, because here the number of parameters is reduced because you are considering only the neighbors. This is one difference. There is a drawback we will consider on it. Second thing is that weight sharing. So you see here, I will give you the things here. See here, I will take it. So weight sharing, for instance, if you are using a kernel, for instance, if you are using a kernel here, you can take a kernel is nothing but a weight, right? So the same weight is used for the first, for finding the pixel of interest value for the first pass. Clear? Here the weight is same. If you take the feed forward neural network, if you go with the feed forward neural network, here here weight will be W1, here weight will be W2, here if you go with weight will be W3. Hope you got the things right. So you need more parameters, right? So you need different weight. So for this layer, for the interconnection between these two layers, W1 you will use. For interconnection between these two, you will use W2, similar other aspect. But if you take the convolution layer, the same kernel is slided horizontally and vertically for the entire, for one epoch. Then there will be a back propagation, learning will happen, and the kernel will be updated. That is, weight is being updated and the things will work on. So here the sparse connectivity is one advantage. Second one, weight sharing. So for the entire image, only one weight is used. After one pass only, you are going to update the weight. So if you take feed-forward neural network, for each and every layer, you are giving it as a layer. For each and every layer connectivity, you are going for the weight. Additionally, bias is also being used. That's why number of parameters in the fully connected or feed-forward neural network is more. So this is how you can relate the convolution neural network operations with the neural network operation. So here, instead of going covering all the pixels, I am going only with the neighbors. This is the one relation you can relate with the convolution in neural network. So second thing I want to know whether it is a static learning or there is any active learning or there in convolution neural network. So first thing, for instance, I have given you the, for instance, I have given this image. This image is decoded into number. So you will get the pixel value. That is, if it is a 3D image, you will have values from 0 to 255. So based on that, you will decode your image into a matrix. So you will, from that, you are going to extract some features and you will saying that this is one of, if I am going with the classification, you're going there. You will apply the default filter. For instance, if any filter is already available, apply that filter. You are saying that this is the monument rather than car, bus, and flower. If you provide edge detector also provides you some of the information, some of the features. Based on that, you are going to classify. Already predefined. If you apply the edge detector. For instance, this is shift and hog are some of the other filters. Hog is nothing but histogram of gradients. Okay, this is same as shift. You can see that shift will give you the values shifted by some range. For instance, I want to shift the pixel value by 5. Either it can be positive or negative. It is up to you. Based on the shift will work. So this is based on histogram of histogram. So you will find what is the histogram of blue, white, and other aspects that are present in the cell, and based on that you are finding. So simply you are applying the filter. Okay, you are extracting the features and providing that these are the class that you have provided. So here there is no active learning. They are learning the things, but based on the filters. So what you need is a back propagation. Once you give the back propagation only, there will be active learning. So in CNN, there is a back propagation. So hope you know what is back propagation, right? We have seen this in the neural feed-forward neural network. After getting the loss, we will back propagate to update the weight. Same thing, after getting the output, test your loss. If your loss is high, back propagate to learn the weights values of the kernel. Okay, so this is what we are going to see. See here, I have given the input. You have applied the filter. It is not that you have to give only the one filter. You can go apply edge filter, sharp filter, and other things for a particular time. At the instant, you can apply more than one filters and get the output of it. And after that, you are testing your thing. If your loss is high, back propagate. While back propagating, what you will happen, you will saying that whether this is working fine or not. If not, update the kernels. So this back propagation helps in the active learning of the features. Okay, that's where the number of epochs plays an important role in CNN. This is not explicitly, you cannot monitor the things what we are done in the feed-forward neural network, but you in feed-forward neural network, you can explicitly visualize what is the back propagation is. But in here, it is very difficult to get the kernel values. Only with the help of feature map, you can say that this is how, for each and every epoch, this is how the kernel has been modified. This can be visualized. So while in the afternoon session, we are going to see the visualizing CNN using Python code. In that, we can visualize how this, after one epoch, after two epoch, how the features are learned. Initially, it will learn a line or any some pattern. After 2 or 3 epochs only, each and every neuron will extract the features and identify some patterns, and it will give you the output. So as I have already told that a particular neuron is responsible for the particular feature in the image. Same thing is applicable here. So this is how the back propagation plays an important role. That's why if you give only one epoch, you will not get the thing. So epochs may, so that's why it is computationally intensive. If you give the number of epochs only, it will try to learn many patterns, then it will conclude with its feature. So number of patterns may combine to give you the features. Based on that features only, it will go with the classification of your output. So we will take a simple example. For instance, if you take this input on how to, we will go with a simple example. If the input is 227 cross 227 into 3 means RGB image, that's why 3. Depth is 3 means if it is a RGB. If stride equal to 4, padding equal to 0, number of filters equal to 96. Can you say what is the output of this? Can you work for a while and can you say what's the output of this? So hope you can apply this formula and you can get these things, very simple only. So have a look on it. So as I have already told that this is a sparse connectivity. It is not that if you go with the MNIST data set, you have to connect all the neurons for a particular thing. Here there is no need. Whatever the neighbors alone. For instance, if you are taking a particular point of interest, whatever the neighbors only you are going to take. So this is sparse connectivity. If you go with the sparse connectivity, number of parameters will be reduced and computation is also reduced. Weight sharing, we have already seen this. Okay. So for instance, one thing is that number of parameters are reduced compared to that of the fully connected neural network. For instance, I am applying more filters. More filters means multiple kernels. So see here, for this data, for this image, I am going to apply multiple filters at the time. So in that case also, number of parameters can be increased. You cannot say that if the number of parameters is decreased, weight update, the kernel updates will be minimal. So you cannot get the output as efficient as was what we expected. This can be avoided with the help of multiple filters. Each filter will contribute for a particular aspect, and you can combine that. You will combine multiple 2D output and you will get the single 3D output. We have seen this in the earlier thing. Okay, next one, max pooling. So max pooling is very important concept, you can say that. So you have a data, you will do convolution. We know how the convolution works. For instance, I have a kernel. This is my image. This is 5 cross 5 image. My image size is 5 cross 5. So this is 5 cross 5. My kernel is 2 cross 2. So when you give the kernel, what will you do? You will find the average of it and you will find the thing. After doing that, you will assume that this is the output after convolution. Please have a look on it. This is my input. I have given some filter. I have given one filter. That's why only one output, right? Then if there are more than one filters, you have another output. So your dimension will be, depth will be more here. So I have used only one filters. Filter size can be of anything. So finally I got this output. So this is my 5x5 is the output after convolution. So instead of going next, what I can do is that in max pooling, instead of going to have 1, 4, 5 and 8 in this kernel, if I apply my kernel on the after convolution, I'm saying that this 8 is going to contribute more to my feature extraction. Actually, these things are always going with the feature extraction only. So compared to these 4 values, this 8 is going to have the maximum contribution to the feature extraction. So why not I have to get all these 1, 4 and 5 instead of taking or keeping only 8. This is what the max pooling is. So now if you slide your kernel over this, you will get the 8 here. If you slide your kernel here, you will get 4 here. If you slide kernel here 7, then 5. So max pooling is you are retaining the thing. See here, one thing, I want to reduce the computation, I want to reduce the number of parameters. But instead of going for reduction of this number of parameters and computation, I should not lose my integrity. So integrity of the image. In order not to lose that, I'm going to take the maximum value, maximum pixel that is contributing to my classification. That is what I'm taking. This is called max pooling. And you have average pooling. In that case, what will you do? You find the average of it and you can go with this value. It is not one, there is only, it is not that there is only max pooling, but max pooling will work fine for the colored image. But if you go with the grayscale image, average pooling works fine. So in average pooling, slide the kernel over your convoluted image, find the average of your neighbors. That is what the pixel of interest value for you. So the next one, how the image classification will be given. So this is the general thing. You have an input, you have some convolution layer. See here, there are n number of filters you have. So you can have pooling because you can reduce the size. See here, it is 28. You can reduce to half. Mostly pooling will reduce the input to half of it. So if you reduce to half of it, computation is also less, and also number of because of pooling, you can reduce the size of it, and the forthcoming thing, the number of parameters will be reduced. So again, convolution is done. If you perform pooling, surely the size of the image will be reduced. I am reducing the size of the image, but I am maintaining the internal aspect of the image as such, because if I go with the max pooling, I am taking only the maximum pixel that is contribute for the feature extraction. Then you have fully connected layers. Those fully connected layers will learn the things and will provide you the output. Mostly if the output is softmax and other thing, if it is a multi-class classification and other thing. So this is what the general architecture of the CNN, any network. You have the input layer, convolution layer, max pooling. The placement of these things may varies. So this is just simply. Finally, you have the fully connected layers. In fully connected layers, each and every neuron will be connected to each other. There is no sparse connectivity here. In this area, only sparse connectivity. Because of this sparse connectivity, you will have less number of parameters. Because of this fully connectivity, this will contribute to more number of parameters. So the number of parameters, you can find the number of parameters. For instance, I am giving you an example how the number of parameters are calculated. For instance, you have taken 32x32 image. Okay, in the MNIST, mostly your grayscale image is 32x32. So here stride is one, number of, I have taken 5 filters. Okay, my K is 6, it means that I have taken 6 filters, each of size 5x5. Have a look on it. My kernel size is, if f equal to 5 means kernel size. Kernel size is 5x5. Padding is 0. So you can find in the parameters. So parameters is nothing but you can find the number of parameters with the help of, you have gone with the filter of 5x5. So 5x5, each will move on it. So you need 5x5 weight. Am I right? So the weight here is nothing but a kernel value. So 5x5, you have 6 such filters. So 5 cross 5 into 6. Okay, 5 cross 5 into 6. If the depth, for instance, if it is a RGB image, depth will be 3. You have to multiply by the depth. Hope you are getting the things right. So here the parameters are nothing but kernel weights. That's it. Kernel values are the parameters. These are the parameters you are updated in each and every layer. So now what you are saying that here, for instance, if here f is 5 means nothing but I am using 5 cross 5 kernel. I am having such 6 filters are there. So what I have to do, 5 cross 5 into 6. So that is what, here the depth, this is a grayscale, here the depth is 1. If you have RGB, you have to give the depth as 3. So that's why 150 parameters. So 5 is 25 into 6 is 150. This is how you have to calculate the parameter for this. If you go with the max pooling, I have given stride equal to 1. I have used, you can change the kernel values. So kernel value, number of filters, stride, padding, these are the hyperparameters. I cannot say that this is the stride, this is the padding. It is a hyperparameter. You can tune accordingly and get the performance efficient from the model. So this is not fixed. For simple case, we have taken stride equal to 1. Here f equal to 2 means my kernel is 2 cross 2. I have 6 such filters, padding is 0. Simply, what max pooling will do, pooling, if it is a max or min pooling, pooling will take our average pooling. Pooling will get reduce the size of the image to half. Now instead of 28, it is reduced to 14. That's it. No parameters, no weight update is there. Am I right? There is no weight update, right? Just you have reduced the thing. You have instead of having the 4 values, you have find either find the maximum value. This is max pooling. If you find the average, this is average pooling. If you want minimum, you go with the min pooling. So if you go with the next convolution layer, you have used stride of 1. My kernel is 5 cross 5. I have used 16 filters now. So it is dependent. For each and every layer, you can specify the filter, kernel size, stride, padding. It is a hyperparameter. So based on that, you can go with that. So this now the parameter is 5 cross 5 into 16. Depth is as usual, and that's why 2400. So the next one, pooling. So here 10 cross 10 will be reduced to 5. So these are the parameters for this convolution operations. Now if you go with the fully connected layers, if you go with the fully connected layers, here what is the depth of it? 5 cross 5, 16 such filters, depth is 1. So it will take this, see here, 15 cross 15 into 16, that is 400, right? So if you have given the depth of 400, in that you are going to have 120 neurons. Have a look on it. It is dependent. This layer is going to have 120 neurons or 100 neurons. This is also hyperparameter. These are the things we can modify according to our application. Kernel weight update is not under our control. That is what the learning thing in the CNN. But you can specify the number of neurons. Here the number of neurons is 120. So what each and this is fully connected. So each and every neuron in this layer has to be connected with the each and every neurons in this 120 in this layer, that is 120. That's why 400 into 120. Additionally, you will have a bias, that is what plus 120. Hope you got these things right. So this is how you will get the values here. So finally, if you are saying that if you want the out, you can specify here in the fully connected layer 2, you can have n number of fully connected layers. So second fully connected layer will have 84 neurons. So what you will have? So 84 into, for instance, for in this case, how this will get the last layer. I am giving the parameter for the last layer. See here, parameter for the last layer is that each and every neuron has to be connected with this. So 84 into 10 plus 10. So this is 850. This is how you have to calculate with this. Hope you know how to calculate the parameters for these things. If you go with the pooling, size of it will be reduced, but the things will be maintained as such.
Excuse me, ma'am.
Yes, ma'am.
Ma'am, could you please repeat that variables S, F, P and all?
Okay, ma'am. Okay, I will repeat.
Yeah, please. Thank you.
see here, F is nothing but what is your kernel size? F is nothing but, I will go with here so that you will get the things here itself. Okay. F is nothing but kernel size. Kernel size means what is the kernel size? For instance, 5 cross 5. If I have given 5 means it is meaning that 5 cross 5 matrix. So K is nothing but number of filters. If you count here, there are 6 filters. That is what the K. S is nothing but a stride. Stride, if you give stride 2 means you have at what interval you have to move the kernel. Now, if you have given stride equal to 1 means it is a meaning that at each interval you have to move the kernel for the adjacent. If you have placed your kernel at the first pixel of interest, second pixel of interest has to be taken into account. So there is no skipping of the pixel. So the input size is retained as such. So this is what the stride. If you want to skip one pixel, you have to give stride as 2. So stride will tell you at which interval you have to move the kernel. How I have to see here, I will show you an example here. See here, this is the stride. So stride will define you the interval at which a filter has to be applied. See here, if you have moved your kernel here, now we are moving your kernel to this place. You have skipped one thing, right? See here, this is my pixel. Now this is my pixel of interest. If you want this pixel to be next pixel of interest, your thing should be here. If
Yes,
you
ma'am.
now,
Yes,
yeah,
yes. Yeah.
no, I have skipped one. Now stride is 2. Because of stride 2, I have skipped one, and now my pixel of interest is this one.
Okay.
That's it. So next one, training CNN. So in training, compared to the fully connected or fast feed-forward neural network, if you see, as of now, I will give you the terminology for feed-forward neural network as fully connected neural network. If you take fully connected neural network, see, this is the fully connected neural network. This is a CNN. In training CNN, for instance, for this neuron, these are the nodes that are contributing for it. So I have to train only these weights. That is the kernels. I have to train those things only. So there is no need for update of weights for all things. See here, in fully connected neural network, each neuron is connected to its adjacent layer neuron. So there is a more weights. So more weights means more training. Here there is only less weights, that to weight sharing. So this is very efficient. Training in CNN is more efficient than that of fully connected neural network, because I'm saying that each and everything is associated with weight. During the training, I have to update the weight. In case of CNN, I'm saying that the same weight is used for one epoch. After that, only another epoch only, after back propagation only, I'm going to update the weight. Here the weight is shared. So in training time for fully connected network compared to that of the CNN is low, because weight sharing and sparse connectivity. Okay. So these are the basics things we have covered. Then we will go into the popular CNN architecture. Any doubts as of now, you can ask me. Any doubts? Any doubts? You want me to repeat the parameter calculation? Anita ma'am, is it fine for you?
Yeah, ma'am, it's okay, ma'am. Yeah,
Okay.
I got it.
Okay, we will break here for 10 minutes. We will resume the session by 11:20. So welcome back to the session again. We will start with the CNN architectures. What are the popular CNN architecture that are available in open source? So there are many things based on the laws. We are going to have the things like GoogleNet, ResNet, and other things. So we will go ahead. So the second part of our session today is what are the popular CNN architectures. So as per survey, so first we have to know what are the tasks, that image task that CNN can perform. So this is a note to you all. First is classification. If you are given with the classification, if you are given with many images, you have to classify whether it is cat, dog, or some other thing. Next one is classification plus localization. Not only finding that whether it is a cat, dog, or that, I want to find the bounded box for that. This is the place, this is the item that are present in the image is cat, and this is the bounded area where my image is present. For instance, if you have a name board, for instance, you have a name board, right? For instance, there is an application in Bharat AI. Hope you have time, have a look on it. They are developing an application. For instance, if you are going in a train, if you are in Tamil Nadu, most of the places and for the train stations, railway stations, you have the name of the railway stations in Hindi and Tamil. I hope so. So if you are moving to some other country, some other state, then native state language will be used and the national language will be used. For instance, in that case, if we are in Tamil Nadu, we know Tamil. If you are moving to Kerala and some other state, their state language will vary. In that case, it is very difficult to identify what is the name of that railway station. In that case, you need translation, right? For instance, if it is in Malayalam, it can be translated to Tamil, then we will get the things out of it. So in that case, I am knowing that this is a signboard. This is what classification. Or I can say that there is a text in the signboard or not. You want to know whether yes or no. Here the classification is binary classification. I want to find whether there is a text in the signboard or not, name board or something. Yes or no, this is a classification, yes. Then I have to find what is the text in that. So what is the text in that is a NLP. I want to process the text in that. First I have to find the bounded box, right? This is the area in which I have to concentrate on it in order to extract the text. So this bounded box is called as finding those bounded box is called as localization. You want x and y coordinate, width and height. Or for instance, this is xy coordinate, you need width and height. From that you can find the bounded box for that image. This is called as localization. Next one, object deduction. So this is with respect to single object. For instance, you are given with the multiple images, you want to find object deduction. In that you can identify the multiple objects in a image, that is object deduction. Then instance segmentation is nothing but apart from that, apart from identifying the image, I want the bounded thing. Not like as such, the instance of that, the bounded area of that image. So those things is called as instance segmentation. Mostly if you go with the Facebook and other things, this tagging, right, they will have a bounded box. This is nothing but an object deduction algorithm. Mostly YOLO is being used. So we are knowing that these are the CNN image tasks. So in that, what are the decisions that I can go with that? So number of layers, this is hyperparameter tuning. So what number of layers, how many layers I have to go for, how many filters in each layers, what will be the filter size? Filter size is nothing but a kernel size. For instance, 2x3, 4x4, 5x5, where I can go with the max pooling. It is not that I can, it is not a ready-made rule that after every convolution you go with max pooling. Not at all like that. It is up to you. You can perform 2 to 3 convolution, then go with the max pooling. It is up to you. So this is an experimental purpose. It is not, there is no proof that this is how you have to do the convolution. This is how you have to go with max pooling. Then you have 4 convoluted, fully connected neural network. This is experimented and tested for the wide range of application. And finally, they have concluded that these are the some of the pre-trained, pre-built network that work fine for the image tasks using CNN architecture. So we are going to see some of the CNN architecture. There are many architecture as of now. This is the earliest architecture. AlexNet is the earliest architecture with 8 layers. Then ZFNet, BGG, GoogleNet, and ResNet. As of now, BGG, GoogleNet, and ResNet plays an important role in today's literature. If you take any image processing article thing, mostly these things: BGG, GoogleNet, and ResNet. These has number of versions based on the number of layers that are present. So these are the error rates. These are the error rates. So as per their architecture design, so if you use VGG, there will be an error of 7.3. In Google, it is 6.7, and ResNet 3.7. This is more powerful CNN architecture. So instead of building this sequential architecture and stacking the layers on it, we can go with the pre-built layer models. Okay. So, but one thing you have to note here is that this is don't go with these things. Now these models are not at all open source itself. From AlexNet itself, these things are present. So it consists of 8 layers. That is one convolution layer, max pool layer. These are called as layers. Similarly, in ZFNet, there are 8 layers. If you go with BGG, that's why BGG 19. You will have a name, right? BGG 19. 19 here is nothing but there are 19 layers. In GoogleNet, there are 22 layers. If you go with ResNet, it is a deep convolution neural network. I can say that it consists of 152 layers. So this is residual network. It works very fine too. We will look onto it with hands-on and also the theoretical part. So now I am going to give a brief explanation on one of these things. Based on that, you can build on the other things. So this is AlexNet is the initial thing. So I will start with AlexNet. Then ZFNet, same thing, only there will be some changes in that. Then BGG and GoogleNet, I will give you how the architecture will be. Then ResNet too. So first we will start with AlexNet. So in AlexNet, you have given the input. Your input size is 227 cross 227. If it is an RGB, you have 3 channels. Have a look on it. Your input is, just have a look on this box, then you will get the things. Very simple thing. Your input is 227 cross. This is how you have to give the input. Although your data set has an input size of 20 cross 20, you have to transform your image into 227 cross 227 if you are going for AlexNet. So in today's hands-on session, we will see that we have to transform our image in order to fit into this model. So this model will accept the image of size 227 cross 227 of depth 3. So this is going to accept the RGB image. So the input is 227 cross 227, 3 means RGB. Next, first layer in that is convolution layer. So in convolution layer, it is using 96 filters. So that's why depth is 96. So depth of the layer, depth of the input is RGB. Depth of the any layer is number of filters we are going to use, nothing but the depth of the filter. So depth of that layer. So this convolution layer is 96, meaning that they are having 96 filters. I'm going to have a kernel of size 11 cross 11, and I'm going to have a stride of 4 and padding of 0. So with this, I can these are the parameters that are I can say that this is a configuration for my convolution layer. So these are user specific things. 96, F is 11 cross 11, kernel size, stride equal to 4 means you are skipping 3 pixels for each movement. So yeah, for each and everything, you are going to skip 3 things. Okay, so then padding equal to 0. Then you can find the parameters, right? As I have already told that my kernel is 11 cross 11. That's why 11 cross 11. What is my depth size of that? That is size of the input is my depth of it. So that's why 3. How many such I have to do? 96. So in this layer alone, I am going to use 34,000 parameters. So I need 34,000 parameter for this thing. So this is how you have calculated the parameters. Here 3 is nothing but, in the before example, my image is a grayscale. That's why 1 will come here. 11 into 11 into 1 I have given. Here this is a RGB image. That's why I have given 3 here. So you can calculate the output. W2 and H2, we have seen this formula, right? Very simple formula. You can understand these things, right? See here, the width minus a filter plus 2p by s plus 1. Same thing. For height, depth is as usual number of filters. So if you apply these things, you will get the things for that. So if you apply these things, this is 227. So with this 227 minus f is 96 plus 2p, p is 0. So the thing divided by 4 plus 1, that is 55. Same thing, H2 55. This is what the output. So output of this layer is 55, 55, and the depth is 96. Are you getting the points out of it? This is after convolution on the input. This is the convolution layer. This is the output you got. This is the input of 227 cross 227 of channel 3 of width 3. After applying 11 cross 11 filter on it, I got a convolution. I got a convoluted image of depth 96 of width and height 55 and 55. So this is what the thing after the first convolution layer. So this is how AlexNet is being designed. Second one is max pooling. So the input to this is 55 cross 55 into 96. So width into height, depth is 96. So now I have used 3 filters, f equal to 3. F is nothing but 3. S is equal to 2, stride equal to 2. Whatever the thing you are using, as I have already told that there is no parameters in the max pool. What you are doing that, now you are going to, this is a max pooling. If your filter is 3 cross 3 filter, we are going to take the maximum thing out of it. So if you are going to take the maximum thing out of it, your input will be halved. So 55 half is 27. So this is what the depth remain as such. Hope you got the things, I think so. So the next one, convolution layer. So the output of this is 27 cross 27 into 96. This will act as an input for this. So 27 cross 27 into 96. Next is the convolution layer. Now I am specifying k is equal to 256, which is nothing but I have 256 filter. Now f equal to 5 means my kernel size, this is 5 cross 5, stride equal to 1, padding equal to 0. So what you will get? So now my number of parameters is nothing but 5 cross 5, each of the depth 96. How many such filters are present? 256. You have 0.6 million. If you multiply this, you will get 0.6. So these number of parameters are needed for this layer alone. So if you want to calculate the output for this, which is nothing but if you have, see here, as usual, W minus F plus 2P by S plus 1. So W here is 27 minus F is 5. So it is 27 minus 5 is 22 by 1 plus 1. So the thing is that if you have stride of 1, just minus, subtract the number of subtract f from the input. So this is 22 plus 1, 23. So this is what now the output is 23 cross 27, 23 into 256. Depth is 256 because number of filters. So always please make a note of it. Depth of the layer is nothing but number of filters. For the input alone, RGB. Next is max pooling. For this max pooling layer, the input is 23 cross 23 into 256. So here max pooling, there is no need for parameters. So what I'm going to do, I'm going to reduce a half of it, going to have a max pooling of here f is equal to 3 means, what is the meaning of f is equal to 3 means, I'm going to have a 3 cross 3 filter. So I will get half of it. So it is 11. It is not 11.5, it will have 11. So the next one, convolution layer. The input for this is 11 cross 11 into 256. The number of filters is 384. My kernel size is 3 cross 3. My stride is 1, padding is 0. So the number of parameters will be 3 cross 3 into the depth of it is 256, 384 such filters. That's why 0.8 million parameters will be used. The output as such. We have seen that 11 minus what is this is 11 minus 3 is 8, 8 plus 1, 9. So the next is also convolution layer. The input for this is 9 cross 9 into 384 is the input. Here the number of filters is 384. My kernel size is 3 cross 3. S is 1. You can ask why S is 1, why K is 34. This is how the AlexNet is being designed. They have went on many experiments. They have decided these with these configuration, this network will work fine with this error rate. This is what the proven concept. Okay. Now we are digging into that architecture and we are saying that this is how the architecture is being made out of it. We have a internal view of that architecture. So now the number of parameters is 3 cross 3. Number of 3 cross 3. The depth is 384. So 3 into 3 into 384. How many such filters? 384 filters. So 1.327 million parameters are required. As usual, calculate the output size of that layer. Next convolution layer, same thing. I hope you know how to calculate the output size and parameters. Max pooling. Okay. With this, we have done all these convolution thing. Now they have gone to a dense layer that is nothing but fully connected layer. So the output for this max pooling is 2 cross 2 into 2.
Excuse me, ma'am.
Yes, ma'am.
Ma'am, you in the output you are using W2H2, no? That what is that 2 indicates?
Ma'am, it is not. This is a W1. See here, ma'am. Right, I will show you the things in this.
The 2 is there any significance for the value 2?
Yes, ma'am. See here. Whenever you are going with the input. For see here, if your input is like this, you can say that the next layer is W0, H0, then W2. You can give the name like this.
Okay, for each layer we give a number like 0, 1.
It is only a naming convention. It is up to us.
Okay, fine. Okay. Thank you.
Okay, ma'am. So we have come, this is the number of convolution layers and max pool layers they have designed. After that, they decided to have a fully connected layers. For this fully connected layers, this is the output 2 cross 2 into 256. In this fully connected layer, they have introduced 4096 neurons. So in this layer, they have 4096 neurons. What will you do? So this layer will have 2 cross 2 cross 256 neurons, and these neurons has to be connected with each other. So that's why 2 cross 2 cross 256 into 4096. So you will have 4 million parameters. So you need 4 million parameters. So next you have another fully connected layer. So here there are 4096 neurons. Am I right? So another fully connected layer, collector layer, it consists of 4096 neurons. So total parameter is 4096 into 4096. So it is 16 million parameters. Next, you have another layer that is 1000. It contains 1000 neurons. So number of parameters is 4096 into 1000. That is 4 million parameters. So this is what the AlexNet architecture is. If you add all these things, you totally need 27.55 million parameters. So if you add all these things, you will get to these things. So this makes the architecture very dense and computational intensive. So even though there is a weight sharing and sparse connectivity, there is 27.55 million. If you think of a fully connected network, each and every neuron has to be connected with each other. If all the things are fully connected, these are sparse connected network. If you go with these aspects, if these yellow and other things, these convolution layers, this is sparse connected network. It is not that it is always connected with each other. So even though it is sparse connected, it is contributing to 27.55 million. All together, it is contributing to 27.55 million parameters. That's why deep learning modules are computational intensive. It has to calculate these number of parameters for each epochs. So that's why computation is more important, or I can say that more intensive in the deep learning models. So if you see here, mostly apart from the convolution layers, this fully connected layer contribute for more than 60 to 70% of the parameters.
Ma'am, one. Can I ask one doubt, ma'am?
Yes, ma'am. Yes.
Ma'am, the total number of parameters is 27.55 M means it's millions, right?
Million. Yes, ma'am.
So that means this many number of features are extracted in the. Is it so?
No, ma'am. No. Number of parameters being calculated.
What is these parameter? Parameter means what? Why we are calculating these kind of parameters?
These are nothing but a kernel values.
Okay.
So each and every time you have to update these kernel values, right? So if you are moving from this layer to this layer, your kernel is changed, right?
Okay, fine. Okay.
It has to be updated. So if you have n number of filters, it has to be updated for n number of filters. That is how we have calculated the parameters.
Okay, thank you.
Any more doubts? That is with respect to AlexNet. If you have any doubts, you can ask me. Any doubts? Can you tell me once again how you did calculate the output? Sir, in which area the output has to be calculated? In which aspect? Either with with W naught and H naught, or are asking number of parameters. How you obtain 4096?
W naught, H naught, ma'am.
Okay, sir. Just a simple formula, sir. W minus F plus 2P by S plus 1. If you apply the formula, you will get the things. I will show you the thing.
Number of parameters, F star F depth into K. Am I correct, ma'am?
Yes, sir. That's it.
Okay, ma'am. Thank you, ma'am.
So you are asking, right? Simple, sir. The formula. If you apply the formula, you can find it logically. If you need, you can go with the formula, sir. It is very simple. This is the formula you have to obtain. W is nothing but width. If it is 227, you have to give 227. F is nothing but your kernel. If it is 5 cross 5, you have to use 5. Padding we have given stride plus 1. H naught, same thing. I will give you an example and work out for this. Sir, I will take this one. For instance, if you take, I will take a small number so that it will see here. So if you want the output, how this 23 and 23 is being derived, I will tell you. And here W is nothing but 27 minus F. F is here is 5. So 20 plus 2P. 2 into 0. So 0 by S equal to 1. S is 1. So plus 1. So W 27 minus 5, it is 22 by 1 plus 1. So 23. Same thing for H.
Thank you, ma'am.
Okay, sir. Sudha ma'am, in which aspect you are asking for how you obtain 4096?
Ma'am, from 2 by 2 you got that answer 4096.
Yes, ma'am. Can you?
In that dense layer.
Yes, ma'am. Yes, ma'am. Have you got 2 into 2 into 256? I think, is there any correction? I think it should be 512. I think so. I think there is the correction. I think this is 4096 means it should be 512. Am I right, ma'am?
No, ma'am.
Simple thing, ma'am.
4 into.
Ma'am, very simple thing. One, you have to multiply this 4096 is derived by 256 into 2 into 2. That's it. If any correction, I will refer and tell. I think it will be 512. I think so.
Okay, ma'am. No, 1024, I think.
Yes, ma'am, it is 1024. I think the value here will be 512, I think so. I have given a wrong value, I think so. I will refer and tell you in the afternoon.
Okay, thank you, ma'am.
Any doubts in the AlexNet? But this is basic net. If you find in any image classification architecture, in any article, this AlexNet is not being used because this is very easy to learn from our perspective for the beginners or thing. For in order to dig the things internally, this is very useful. Next is very interesting thing, BGGNet. So here one thing, same BGG is simple thing. Whatever you have seen here is same BGG AlexNet architecture is used. If you see in the AlexNet architecture, the kernel size may vary in each and every level. Initially, you have used 11 cross 11, then you have used 3 cross 3, then you have used 5 cross 5 like this, right? But they made some changes. Throughout the thing, they have used only 3 cross 3. This is the one change. So the total number of parameters in non-FC is non-fully connected. These are the non-fully connected layers. These are fully connected layers, right? In non-fully connected layer is 16 million parameters. Total parameters in the fully connected layer. See, this is 512. So the final output of this is 512 cross 7 cross 7. This is 7 cross 7 into 512. If you have 496 neurons in the fully connected layer, this become 4096. So 7 cross 7 into 512 into 4096. Another fully connected layer. So 4096 plus 4 into 4096. You got the things, hope so. Next one plus you are going with next thing 4096 into 1024. This 1024 is nothing but in the softmax layer, you are going for an output, right? Instead of 4096, I am going for a 1000 thing. Additionally, they have used the 4 neurons for triggering the certain features. That's why the 24 neurons are being used for this. That's 4096. And instead of 1000, they have gone for 1024. So these are some of the changes they have done from the AlexNet. Please have a look on it. Same architecture, same thing. They have given the changes. I have given only the changes and architecture. I have not detailedly explained. Same thing. So total number of parameters in the fully connected layer is 122 million parameters. So that too, in the first fully connected layer, it accounts for 1 or 2 million parameters. If you go with this, see here, your image, the one thing, it will accept 227 cross 227 cross 3 input. If you go with the VGG, it has to be 224 cross 224. Whatever the size of your image may be, if you are going for using VGG model, you have to transform your image into a size of 224 cross 224. Here the width is, see here, I will explain you. Here the width is 3 because the input is RGB, so width is 3. So they have 2 convolution operation side by side. So it is not that convolution then max pooling, convolution then max pooling. It is not at all needed. They have done 2 convolution then max pooling, then 2 convolution max pooling, 3 convolution max pooling, like that they have done. If you want, if you in a research aspect, I will tell you the thing. You can get the research things out of it. It is not that take the VGG net as your thing. Given a data set, find the accuracy thing. For instance, you can change these things, right? Change 1 or 2 layers and test for the data. This becomes a research, right? You have built your own architecture. You have built your own stack on it. You can find the things out of it. So in the hands-on session, in the first session of today's afternoon session, we are going to have a sequential model. In that, we are going to build our own model. Rather than using the built-in model, we are going to build a model. So in that case, what you can do is that take the VGG model itself. You can get the model parameters with the help of printing the VGG. You can get what are the things, you can get these things. What are the basic parameters I have used for building this model? For instance, I am saying, see here, my input is 224 cross 224. Here 64 means what is the meaning? Throughout my F is 3. Am I right? My input to this is 224 cross 224. My width I have given is 3. Now I have used 64 filters. So here my configuration to this convolution 2D, I have to give some parameters. Here the parameters is nothing but the input is 224, 224. Here the K number of filters is 64. F is equal to 3. This is a default. You have to define what is stride and padding. These things you can get from these things. For instance, additionally, you are adding one convolution layer here, removing one convolution layer here, additionally adding one convolution. Test for this. It may work fine for your data because depends upon the nature of the data only it is going to work. And also see here, it is not that you have to use 4096. This model has used 4096 parameters. You can reduce the parameters or you can increase the number of neurons in this stage, you can work on it. So these are the things we are going to see this. You can custom your model, you can work on it. So based on these things, you can go with the research aspect. Any doubts in this, ma'am? This is what VGGNet. Hope these things are fine. Same, whatever the thing I have given you in the AlexNet, apply these things, you will get the things. This is how the parameters are calculated and the output is given. You can visualize this output also in the Python. Any doubts?
Is there any special reason to fix the kernel size 3 by
Ma'am,
3?
if the kernel size is 3 by 3, you can capture the more intense pixels of the image. If you go with a bigger kernel size, you will have the average value, or I can say that because you are going to add and get the values right, it will not contribute for your image classification task. If you go with a smaller kernel size only, it will give the feature extraction more perfect. Always try to have a smaller kernel size.
Okay. If any possibility to fix the size below this one, 3 by instead of 3 by 3, if I am going to cross 2 in the sense.
Yes, you can give it.
How it?
In the parameter section, you have to give it as 2 cross 2. That's it, ma'am. In the afternoon, we will write a code on that. In that, I will tell you if you. This is user specific. This is a hyperparameter.
Okay, ma'am.
Hyperparameter, you can test on it.
Okay, thank you.
Any doubt? Okay, next comes the very important thing. I can say that GoogleNet. This is I can say that this is the deepest architecture according to me, rather than that of the ResNet. Google has given a deep learning architecture that is called as GoogleNet. And the background thing, I can say that the core concept of this is 1x1 convolution. So you have seen 3x3 convolution, right? If you are clear with 3x3 convolution, can you say what is 1x1 convolution? So 3x3 convolution means you are going to place the 3x3 kernel on your image. 1x1 convolution means you have only one cell. The pixel itself is going to be your area of interest. There is no neighbor at all. Am I right? This is going to be 1x1 convolution. This plays an important role in minimizing the number of parameters. So we will see this. So this 1x1 convolution is very important because in each and every convolution layer, we are not going with only one filters. We are going for 512 filters. We are going for 284 filters, 320 filters, and so more or less these filters will be of homogeneous type, not of heterogeneous type, because convolution is used to extract the features out of the images. So mostly it is homogeneous in nature. So what I can do is that, so if this is my image, if this is my 3D image, what I will do, if it is a 2x, assume that if it is a 2x2 kernel means, I will move this kernel first in this 4 cells, next to the 4 cells, next and horizontally and vertically. This is what I will do. I am not going to the depth wise. See here, I have go with the length, height and width, not with the depth. We have already seen this. There is some work going on this, how to go with the depth and get the capture the features also. But as of now, these BGG and other open sourced model will go only with the 2D aspect. In 1x1 convolution, this is what my kernel is now. Am I right? Because this is 1x1 kernel. So 1x1 convolution is kernel is 1x1. So now I have my kernel size is 1 cross 1. I have to move each and every kernel. Am I right? But instead of going to navigate these two, all the here the filter is, you are having 192 filters, width is 64, height is 64. This is what the configuration of this image. Am I right? You any layer, I can say that any layer or any image, or I can say that mostly this is layer. If the image, if this is the input, means this should be 3. Am I right? So this is the output of any convolution layer or anything. So this is 64 cross 64. You have 192 filters like this. So what I can do that, I have already said that these filters are of homogeneous nature because the number of filters are increased to extract the exact features. Because one filter may be working with fine with some other thing, another filter may be working with nose, another filter may be working with ear of the image. So that is how the image has been done. So we have already seen that you can apply blur filter, sharpen filter, edge detector on a go. So each one will have its own capability, they will work on it. Okay, so see here, this is going to work on it. Now you are going to get the value out of it. So you will take this 192, this first pixel alone, take this average of it. This is going to be the value for this first pixel. This is what 1 cross 1 convolution. 1 cross convolution is applicable in order to reduce the depth of it. Am I right? Now the depth, instead of 192, you are having the depth as 1. So instead of having depth, if the depth is more, I can say that if the depth is more, the number of parameters may also increases. This is one way of reducing the depth. Okay, if you reduce the depth, number of parameters is reduced, your model is efficient, but you are extracting the things out of it. So mostly, so this is how. So you are taking first pixel in one each and every 192 filters, taking the average of it. That is what going to be the value for the first pixel. This is what 1 cross 1 convolution. Now your depth is only 1, not 192. So this is 1 cross 1 convolution. This made a revolution. I can say that this made a revolution in the deep learning with respect to image processing. So the next, as usual, these things, hope you know these things, right? Stride, 3 cross 3 padding, same thing. You can go ahead with this. This is what the Google net. I have given you a simple thing. So I have applied the filters 3 cross 3 convolution and other thing. You can, it is not that we will go with this. Okay, we will go with. So 1 cross 1 will convolution will reduce the depth. So it have less computation. For instance, it is not that you have to go with only 3 cross 3, you have to go to only 2 cross 2 convolution. You can go all the way along it. Finally, you can go with the 1 cross 1 convolution in the same manner as such of 3 cross 3 or 5 cross 5. Okay, so now you have done 5 cross 5 convolution, then you have done 3 cross 3 in a parallel manner. So in 1 cross 1 and 3 cross 3 max pooling. I will give you the thing. This is the you will get the things when you have the inception model. If in PyTorch or any TensorFlow, any library, if you refer in the internet, you will find only inception model, not Google net model. The model name is given as inception. The core module of that Google net is inception module. We will see what is inception module. First, what you are doing, saying that you are applying first thing. So they are first, the image is 28 cross 28. Okay, the image is 28 cross 28. The depth is 256. Okay, depth is 256. What will happen? They have given 1 cross 1 convolution. Because of this 1 cross 1 convolution, you have reduced the thing. Okay, so you have 96 1 cross 1 convolution. I will tell you what is this 96 1 cross 1 and other things. Next, I have given you, I have applied multiple things. See here, in a thing, this inception module will take multiple things and give you the aggregated thing out of it. Then 128 into 1 cross 1 convolution, this will reduce the depth. Then 32 into 1 cross 1 convolution, so it will be reduced. Here 32 is nothing but you have 32 filters. Then 3 cross 3 max pooling, so there is no reduction in the number of things. Next, I have done 96 filters with 1 cross 1, each is doing 1 cross 1 convolution. Then from here, from 128, I have done 192 filters with 3 cross 3. 3 cross 3 convolution I have done, then 96 5 cross 5 convolution, then 64 1 cross 1 convolution. You may ask why 96, 192, why 96 and other aspect you may ask. They have designed these things like this. They have proven that this is how with this the error rate is being reduced compared to that of the VGG and AlexNet. It is their design module. One thing I want to insist here, kindly wait for a minute. After completion, you can, this may look vague as of now. I will complete the things of the Google Net, then you will get the clear picture out of it. Now my input is width and height will not change at all. Width and height will not change at all. One thing, I can reduce the depth of it or I can increase the depth of it. It depends. So if you want to reduce the depth of it, you have to go for 1 cross 1 convolution. So if you go with a 1 cross 1 convolution here, in this inception modules, the number of parameters will be reduced. Even though you have done, but in each 1 cross 1 convolution, the number of parameters will be reduced, but you are going for many operation like this. It is not that I have already told that it is not that you are doing only 1 cross 1 convolution for each step. You are doing in parallel. In parallel, you are doing 3 cross 3 and 3 cross 3 convolution and 5 cross 5 convolution. You are doing all these things and finally getting the output of it and going to add these outputs, and you are saying that this is going to be the width of my output is. So if you see here, so this is 96 cross 1 cross, I have done 1 cross 1 convolution here. So I have 96 filters. Okay, you have reduced the depth of it. In see here, if you have 128 filters and if you have reduced the if you perform 1 cross 1 convolution, you will reduce the depth. Similarly, 32 in then you have max pooling and other things. The thing is that if you add these things, you have to get these things. I think if this is right or wrong, you will check on it. The width and height is maintained. The depth is dependent on the inception module's output. Multiple things are done at a while, you will get the thing. See here, I will tell you. First, you will take the input. I have given you a detailed explanation on Google Net. First, take your input. So your input is here it is 229 cross 229. I have taken the simple example of it. If this is an inception model, you have see here. First, this is input. This is 229 cross 229 into 3. Then you have gone for the convolution and with the 64 filters with some padding and stride, you got 112 width and height. Then you have gone for max pooling, then convolution, then max pooling, then they have gone with the inception model. See here the width is 192. Am I right? Here the width is 192. Here it is 28. Here it is 28. So sorry, this depth is 192. Width and height is 128. This width and height is maintained as such. If you see here, the depth is increased to 256 because see here, what is the output of here? This is 28, 28, 192. I have taken 28, 28, 192. And now this inception model is internally working and going to extract some features rather than that of the convolution. They are going to perform multiple convolutions here. So what first it will do? It will do a 1 cross 1 convolution. Okay, because of this 1 cross 1 convolution in 192, here 192 filters are there. Instead of that, you are going with 96 filters. So now your depth is 1. So you have 96 cross 1 cross 1. Next, what you have done, you have made a 1 cross 1 with 16 filters. Then you have done a max pooling. Directly you have done with a 64 of 1 cross 1. After performing this, you have done these things. Same here, convolution, these things. If you add the 64, 128, 32 and 32, you will get the 256. So the insight in the inception model is that in each and every model, what will we do? Either 1 convolution or 2 convolution only. Am I right? If you see this network, either one convolution or 2 or 3 convolution only do the same operation you will do. In VGGNet, if you take a particular thing, either convolution or max pooling, these things you will do. But if you take the inception model, it will do the combination of all the things. It will maximize to extract the features at a while. So in this case, even though here the depth is being reduced, here they have with the less number of parameters because of 1x1 convolution, they have extracted more features, and finally they will give you the output. If you add all these things, 64, 128, 32 and 32, you will get the 256. Yes, are you getting the things? This is how inception model works. Inception, it is not that only you have to do convolution or max pooling. It will do convolution, max pooling, 1x1, whatever the thing they are needed. This is their spec. According to GoogleNet, this is their spec. They will do that because they are doing convolution, right? During this convolution, they don't want more number of parameters. See here, if I go with 192 means 190. What will be your number of parameters is nothing but kernel size into number of filters. Your number of filters plays an important role in the number of parameters. In order to reduce that only, they are going for 1x1 convolution. So they gone for 1x1 convolution, extracted the features with more number of filters. 96 filters are doing the same thing. They will try to get what are the available features in the images. They will extract the, I can say that mostly they will extract the features out of the images. Again, they will do many operations, and final outcome is based on the sum of these things present here. So if you see how 256 is arrived is 64, 128, 32, 32. This is what the inception model of this 3A is nothing but internally this is what happening here. So next, if you go with the 3B, same thing. You have taken 28, 28, you have with depth is 256. See here, now instead of 32, they have gone with 96. It is their specification. Again, I am saying that this is not fixed. According to these specification, they are saying that the error rate is being reduced to this much. There is no clear insight that this is the number of filters you have to use, this is the stride you have to use. It is not at all defined in any literature. It is their spec. They are saying that with this specification, my model is giving this less now error rate. So this is what the inception model of this. Then max pooling, hope you know that same 480 only with a reduced number of parameters. Then again 4B, same thing. See here, now it has been increased to 208. There is no question of why 208, why 192, why 64. It is their architecture. If you want, you can build your architecture, write your own inception model and test on it. So that's why opens deep neural network, mainly convolution neural network. Most of the models, I can say that almost all the models are open source. You can experiment on this. If you know these things, internal things, you can work on it on your own. Same thing. Instead of, see here, instead of max pooling, they have gone for average pooling. So they have done different thing. Trying different is the important thing, right? They will check whether things are working fine or not. Then they have two fully connected layers of 1000 and 1000 each. That's it. This is what the GoogleNet architecture is. Here inception plays an important role. In that inception, not only convolution, they are performing convolution, max pooling and other thing with 1x1 convolution. This is very important. They are performing all these things with 1x1 convolution. Because of that 1x1 convolution, they are going with less number of parameters. And they are extracting the features more with their specified depth. So even though I am saying that this is a large network, I can say that this is a dense network. If you compare with this, I want to give an example in that. In the last slide, I have given thing. Okay, this is an image that is given by Google for their GoogleNet. So in GoogleNet, see here, these are some of the convolution. We have seen these things, right? Have a look on it. This is the final GoogleNet architecture. Before that inception, you have these things, right? Convolution, max pool, convolution, max pool. Then you have inception. So these are the things that are present. You can see here, convolution, max pool and other thing. See here, this is an inception model. In that inception model, you can see that parallelly you are working on it and you are concatenating. That's why I have told that how the depth will be here, and they will, you have 3 inception, then you have a max pooling and other thing, then inception. In that, they will take another thing called auxiliary loss. This is very important. None of the architecture has taken the loss in the intermediate part. If you see in any literature, none of the architecture has taken loss at the intermediate part. They will provide you loss only at the final. After fully connected layer only, they will provide the loss. But GoogleNet alone have taken the auxiliary loss. This in this point, I am going to calculate the loss. I will back propagate it. So in this area itself, I am trying to reduce my error instead of going along, because this fully connected layer itself contributes for many parameters. Hope we have seen this, right? So this is one disadvantage. So in order to avoid this advantage, at the intermediate point, I have taken the auxiliary loss and find whether my loss is acceptable level or not. If not, I will back propagate it. You may ask why here, why not here, and other thing. I am again saying this is their design spec. They have tried these and given things. Okay. So if you compare with AlexNet, so 12 times less parameter than AlexNet, but 1 time more computation than AlexNet. So AlexNet is very simple, right? Very simple thing. AlexNet is very simple architecture. I cannot say that it gives the more accuracy for the image classification. But it provides improved performance on ImageNet because of its auxiliary loss. This is one of the salient feature of auxiliary loss. You can visualize this model using Python, whether it is auxiliary loss or not. In this intermediate point, you can take the loss for instance, if you take the CIFAR 10 data set, there are 10 classes. Get the loss of the 10 classes. If you are saying that it is at the appropriate threshold level, go ahead with the next thing. If not, back propagate it so that your loss at these things will be minimized, and also number of parameters will also be reduced. That is what the thing we have given. So this is what the GoogleNet. Next is ResNet. Here it is very complicated, but it is very simple. So if you compare with the VGG19 means you are having 19 layers in that. So in ResNet, you are going to have a ResNet is nothing but residual network. I will give you the core concept, then you will get the things out of it. So this is plain. If you have 34 layers means each layer's output will act as an input to this layer. This is how the things will be processed. We have seen all these things, right? Output of one layer act as input for the next layer, and same thing will process up to the fully connected layer and the output layer. One changes what you have done here is that because of convolution or because of some max pooling or because of some other operation you are doing, the original aspect of the previous layer may be detained. So in order to overcome that, what I am going to that, whatever operation you are doing on my data, go ahead. In addition to that, I am giving my original data. That is what the residual network. See here. So this 3x3 convolution 64 will give you the, will act as an input for this layer. Okay. This will act as an input for this layer. Apart from that, what it will do, so this will do some operation and there will be some output. Apart from this output, what I am saying, combine this output, initial output. So my originality is always preserved. In addition to that, your operation is also done with that. So with this, I am saying that if any of the intermediate layers is degrading your feature extraction, that will be prevented here. So this is how the residual network is done. This is not in 1 or 2 layers. This is 34 layers. As you have seen in the previous first slide in the literature, there is a depth up to 152 layers. This is how the residual information is added with the original information and passed on to the next layers. This is how some neurons in the previous layer may be well in enough in deduction of some features, while this has been eroded because of my spec. For instance, I have given some of the filters like 36 filter, 100 filters, or I have given a stride. If I have given the stride, that pixel itself may have been omitted. In that case, my feature has not been taken into account. If you give more stride, you are saying that you are going to skip the pixels. In this case, your futures will be destroyed. In order to avoid that only, this residual networks plays an important role. Okay, if you see the ResNet, it comes with maximum. I have told that it is 152. This is ResNet 51, 101, and 51 are present. So this ResNet, I can say that this is the most powerful app. GoogleNet is good with respect to performance, but ResNet is very computation intensive. Hardly it will take at least 5 to 10 minutes to train itself for the CIFAR 10 dataset. So if you go with many ImageNet dataset, it's very difficult to train the ResNet. But if you go with the GoogleNet, it is very efficient in computation because of the auxiliary laws at the intermediate stage, because less number of parameters will be there, so less computation, but this is very computational intensive. So there are 3 versions of ResNet available: 51, 101, and 152. So this will work for all these things: classification, localization, deduction. And this is COCO deduction and segmentation. This is ImageNet is nothing but a data set. For this ImageNet dataset and COCO dataset also, it's work very fine with improved efficiency. So with this, I have completed the architecture. I think you may have doubt in the inception layers of the GoogleNet. I am very sure of it. In the afternoon session, I will visualize the model, then get the things out of it. Because time is running out, I have to give the visualizing CNN. Okay. Okay, as I have already told, in the fully connected network, each and every neuron is responsible for a particular feature. I have already told that this neuron is responsible for recognizing eyes. This neuron is responsible for recognize ears, nose, and other thing. Same thing, this is applicable here, only sparse connectivity and weight sharing. So each and every neuron will have its receptive field. So how you can find this? So this is a neuron that is help in identifying the dog. This is the neuron that is help in identifying the flower. So you can go with this. For instance, they have given an ImageNet data set. In that ImageNet data set, they have identified that a particular neuron is responsible for identifying. If you have given an image of, in this class, if you take this task, if you take this image detection task, you are given with an image. So in that, you have to find whether this is a dog, cat, or a duck, or other thing, right? So they have identified that neuron 1 is always going with the neuron 1 will fire if that image have a human. Neuron 2 will fire when you find it's a dog image. Similarly, flower and other thing. This is how each and every neuron will make itself as a responsible for a particular feature. They become the receptor for a particular feature, and it will fire once it finds a feature on that particular image. So there is a disadvantage of this also. If this neuron become dead, it is very difficult. For example, the flower neuron becomes dead. For instance, I am saying that this become a problem. Even though if you have given an image with a dog, flower, and human and dog will be correctly identified, detected, but flower will not be detected because other 2 neurons do not know how to detect the flower. This neuron always helps in the overall classification or reduction of the objects. So this is a problem. This is overcome with the help of dropout. We have seen in the yesterday's session, right? Dropout plays an important role. In that case, what we'll do? Other neuron also try to learn the features of the flower. They also cooperate in the detection of the flower. So, but we should not do these things because each neuron will place an important role. Our major goal is to find the accuracy of that. So, in order to that, you can test the receptive field of the neuron. For that, you have a occlusion experiment. We will see that in a hands-on session. See here, the math behind that is, they have given a math behind that. For instance, this is the input x1, x2. For this one, assume that this is the input. This is the kernel. So assume that this is x1, x2, x3, x4. This is the kernel as it is a weight w1, w2, w3. How will you find the value of this particular pixel? Same thing, W1 into X1, W2 and X2, same thing we will do on this. Then this is nothing but weight, vector product of a dot product of weight into X matrix. Am I right? How they have internally they have done is that with the help of a thing, with the mathematical concept of cos theta. When cos theta will be high? When cos theta will be high? If the angle between them is 0. Am I right? It means that when W and X are in the same line, okay? If W and X are in the same line, the angle will be 0. If it is a unit vector, I am saying that it is in the same line. In that case, the neuron will be fired. So the thing is that if the input and the weight are concentrating on a particular feature, then you are saying that they are going to fire, the neuron will fire. If your weight in the kernel and the data, I mean X1, X2 values, that means pixel value also matches with the intensity of that color, it is saying that that feature will be extracted and the neuron will be fired. You have the good classification. This is the math behind the firing of neuron. Based on this, receptive field of the neuron can also be found. So when you find this for the first pass, for instance, if you have applied a first convolution layer, you will find this. They will find this layer. This is what the after first convolution. For instance, I say that after first convolution layer, they will get a image like this. This is called as feature map. So this neuron is good in identifying these colors. This neuron is good in identifying these stripes, these patterns. So first they will good in identifying the patterns, then patterns will make you the images. Not at a stretch, it will not find the image. First they will identify the pattern, then pattern, they will combine the pattern, then they will extract the image. Okay. So this is occlusion experiment. We will see this in the demo session. So occlusion is that, for instance, this is a heat map. Hope you have heard this in the heat map. Many in statistical analysis, we will go for the heat map. In this heat map, this blue region saying that because of this, blue is saying that this will contribute more for your task. For instance, if it is a classification task, here classification task, here true label is Pomeranian. In this nose plays an important role in identifying this Pomeranian. All other things does not play an important role. So these neurons are fired at most. That's why it has high value. That's why this color is blue. Here high value means color is blue, same thing. Here the true value is car wheel. See here. So these neurons will have the high intensity. Similarly, the dog. Why there is a blue here is nothing but in the neuron has learned this dog with human. Sometime, mostly in a picture, you have given a picture. In that picture, most of the time the dog is associated with a human. So they have learned a feature like this. That's why blue color here. Okay. This is so. For instance, if you have made a patch here, for instance, in this patch, this gray patch, if you have given your probability distribution, I can say that if you apply the softmax, your output will reduce to a large extent. For this, in this case, if you have given the softmax of 0.7 means it is close to the true label. In this case, if you made a patch here, in this area, if you made a patch, surely your output will be reduced to 0.2 or 0.3. From this, you can note that this is the area of interest for us. We have to concentrate on these neurons. These neurons extract those features. Okay, so that's all from my side. If you have any doubt, you can ask me. With respect to inception model, you will be clear in the afternoon session because it needs detailed explanation on this. That's why in the hands-on session, we will work on it. Any doubts, you can ask me. ResNet 1.1, so same thing. Instead of layers 51 or 52, you will have 101 layers. We need, okay, I will come from, do we need GPU? Yes, you need GPU. We will work on GPU only. In the afternoon session, we will enable the GPU and we will use two device method to go on with it. So as of now, I am not concentrating on deconvolution. So ResNet 101, same thing, you can use it. Only thing, instead of this 52 layers, you are using 101 layers. That's it. Just you have to use that model, sir. There is no need to define all these layers. Model is already there, and you have predefined model also, pre-trained model also with the weight itself. There is no need for you to train the weight also. So there is no need to run the thing for many epochs. Pre-trained model is also present. You can go with that. Sure, ma'am, I will share my PPT. Any more doubts? Or any misinterpretation by me? If so, you can give me so that I will also have a look on it. Thank you so much. Shanti ma'am.
Thank you, Tamil, for your nice session. We will meet again at 2 p.m. Thank you, participants. Feedback link is shared in the chat window. All are kindly asked to fill the feedback form. Also, while you attend that, you ensure that whether your mic and camera is in mute or not. Thank you.